Welcome back to Laplace transform part 2. In part 1, we have already studied what is the basics of Laplace transformation, existence of Laplace transformation, and we also studied Laplace transformations of some basic functions, and we have seen some properties of Laplace transformation. We have covered linear property and first shifting theorem in part 1 lecture. So let's start part 2. Today we will see some more properties and more results on Laplace transformation. Let's start. Change of scale property. If Laplace of ft is fs, where s is parameter, is greater than alpha and alpha is exponential order of given function. This means Laplace is existing here. Then Laplace of f into at, if we multiply with some constant to the variable t, then its Laplace will be 1 over a f of s over a, where a is greater than 0. A is greater than 0. Let's see the proof. What is given to us? Laplace of ft is given to us capital Fs, which is given as 0 to infinity e to the power minus st ft dt, and it is given as Fs. How we are selecting s here? It is a coefficient of t with the minus sign, because then only this improper integral will exist or will be convergent, and s is positive here obviously, then only e to the power minus infinity will converge to 0. You can see my improper integral lecture also. Then Laplace of f of at will be 0 to infinity e to the power minus st f into at dt, provided we can write here fs with two conditions. When t has coefficient 1 and here t has coefficient s, then it is equal to fs. This is the standard definition of Laplace transformation. So for converting in the standard definition, we have to make this coefficient the variable coefficient 1. So we will replace at by some v, 1 into v. Then the coefficient of v will be 1. See, t is infinity, then v will be infinity, and t is 0, then v will be 0. That's why we are taking a positive, because it will go to infinity only. If a is negative, then it will go to minus infinity, and our integral will not be converged in that case. E to the power minus, put the value of t, it will be v over a into s f of v. What will be the dt here? Dt will be the dv over a. We can divide by a in the denominator side. So dv by a. Now Laplace of f of at will be 1 over a. You can take outside, 0 to infinity e to the power minus s over a into v, because the variable is v now, fv dv. See, s is positive, b is positive, because v is belonging in 0 to infinity. That's why a must be positive here. Then only this integral will exist. Now, if you see this type of definition here, the coefficient of variable is 1, and what is the coefficient of v here? S over a. So it will be the f of s over a. Here it is s only, so it is fs. So this is the Laplace of f of a. So this is called change of scale property. Change of scale property. You can multiply with any positive constant in t variable, and you can find directly that the Laplace transformation. Okay, we will see example based on this also later. Or you can see here only, if Laplace of e to the power t is 1 over s minus 1, then what will be the Laplace of e to the power 2t? Nothing. Here you are changing, you are multiplying with a equal to 2 here. So it will be 1 by 2 into 1 over s by 2 minus 1. You have to replace by s by 2. For here you have to replace s by 2. S by a you are replacing and you are dividing by 1 over a. Here a is equal to 2. So it will be 1 over 2, 2 over s minus 2. So the Laplace of e to the power 2t will be 1 upon s minus 2. So this is another way to find the Laplace of e to the power 2t, or you can find by directly the formula I discussed in the previous lecture, or you can use the change of scale property also. But this property is useful for difficult functions. Suppose you have the Laplace transformation of greatest integer t and you want the Laplace transformation of greatest integer 5t or 7t, then this property will be very helpful. So we will see later in this lecture what is the use of this property. Next property we have multiplication by t to the power n. Multiplication by t to the power n. So if Laplace of ft is capital Fs, then if we multiply where s is greater than alpha and alpha is greater than equal to 0, then the Laplace of t to the power n into ft, if we multiply t to the power n, it is minus 1 to the power n, nth derivative of Fs. Remember here n is here 1, 2, 3 and so on, any natural number. Or particular for n equal to 1, what will be the result? Laplace of t of t means multiplication of t. If you use n equal to 1, its property will be multiplication by t only, because you are using n equal to 1. It will be minus d by ds, because minus 1 to the power 1 will be 1 only, Fs. So this is also a very, very useful result. We can prove also, we can prove this also. I'm going to prove for n equal to 1. Similarly, you can prove for n using induction or any other way. So let's start with RHS. Minus d by ds of Fs. What is your Fs here? Fs is nothing else, it's a Laplace transformation of ft that is defined as 0 to infinity e to the power minus st ft dt. So it will be 0 to infinity e to the power minus st ft dt, and you want to differentiate it. So how to differentiate with respect to s over integration sign? So for this we have very famous Leibniz rule, differentiation over integration. First kind of Leibniz rule I taught you in the limit chapter and integration, but we have second kind also. Suppose you want to differentiate phi x to psi x, ft dt I have already told you, but if inside function is a function of both the variables t and x, then how you will tackle this type of problem? So then this is method is, you know, upper limit in the place of t, upper limit in the place of t, d by dx of upper limit minus lower limit in the place of t, d by dx of lower limit, plus there is a one more term if inside function is depending on both the variable. Up to now I have studied only it is depending on t only. That's why I told you this method, this term. But if the function of both the variables, then it is phi x to psi x. One more term we have partial derivative with respect to x, ftx of this function into dt. So here you can see that inside we have both the variable s and t. So you have to use this method of Leibniz for differentiating it. You can see that upper limit and lower limit both are constant. It means its derivative will be 0. So these first two terms will be 0 here. Only this term you will get. So it will be minus 0 to infinity del by del s. The function we have s only, we have to differentiate e to the power minus st ft dt. E to the power minus st ft dt. We have to differentiate only the function which have s. We will get only this term because these two terms, due to these calculations, that these two terms will be 0 for this integral. So you will get it is equal to if you differentiate e to the power minus st with respect to t, you will get minus e to the power minus st and the coefficient of s is t. So the derivative will look like now it will be I'm writing here. It will be minus 0 to infinity minus t e to the power minus st ft dt. So it will be 0 to infinity e to the power minus st into t of t dt. You can write like this, minus minus plus, and this is nothing else Laplace of t ft, because this function we have in the multiplication of e to the power minus st. So it's a Laplace of t into ft. That was the LHS. So this is the proof of multiplication by t to the power n. Let's see one example based on this result. This is very useful property. Suppose you want to find the Laplace of t sine 3t. You want to find the Laplace of t sine 3t. Find Laplace transform of t sine 3t. So you can see it's a multiplication of t in this function sine 3t. Let's see what is the Laplace of sine 3t. So remember my lecture 1, I told you Laplace of sine 80 was a over s square plus a square. Here a equal to 3, so it will be 3 over s square plus 9. So it will work as fs. Now the Laplace of tft I told you is minus d by ds of fs. So Laplace of t sine 3t will be the minus d by ds of fs. What is fs here? 3 over s square plus 9. You have to differentiate it with respect to s only. So s square plus 9 whole square, if you differentiate it, you will get it is 6as over s square plus 9. So this is the Laplace of t sine 3t. One very famous question asked in the GATE exam and many engineering exams also. What is the find also 0 to infinity, find also 0 to infinity e to the power minus t sine 3t dt. We cannot find this integration using integration by part, but with the help of Laplace we can find it in very quickly. So you have Laplace of t sine 3t, and what is the Laplace of ft is? Laplace of ft is 0 to infinity e to the power minus st ft dt. So Laplace of t sine 3t will be 0 to infinity e to the power minus st t sine 3t dt, and it is obtained by you 6s over s square plus 9 whole square. Now you see the question. T sine 3t you want in the integration also, but here you want e to the minus t only, but you have e to the power minus st. You just replace s by 1, both side, you will get the required value of integration e to the power minus t sine 3 dt will be 6 over 1 plus 9 means 10 whole square. So it will be 3 by 50. So the value of this integration will be 3 by 50. So for finding some very difficult improper integrations, Laplace transform will give you a good idea to evaluate that difficult integrals. We will discuss that in detail also in later classes. I'm giving you some homework also using this property. Homework. Find Laplace transform of, first I am giving you t sine 4t, t sine 4t. Second I am giving you t square cos 3t. You have to 2 times differentiate fs. And third I am giving you t to the power 5t. You can use solve by any of the method. You can find it by shifting property also, because you have exponential function. Fourth I am giving you t square e to the power minus 2t. So these two can be solved by shifting property also, but for these two problems, first and second, you have to use multiplication by t to the power n property. I am giving you answer also. The answer of this problem is 8s over s square plus 16 whole square. Answer of this problem is 2s s square minus 27 over s square plus 9 whole cube. And the answer of this problem is s minus 5 whole square. And answer of this problem is 2 over s plus 2 whole cube. So these are the answer and homework for you. Let's see next property. Division by t. We have studied what is the effect by multiplying by t power 1 or t power n. Let's see what will be the effect on the Laplace transformation if we divide by t. If Laplace of ft is capital Fs, s is greater than alpha, alpha is greater than 0, then Laplace of ft over t, if you divide by t in the entire function, it is nothing else, it's the integration of s to infinity fs ds. In the previous property you have to differentiate fs, but here you have to integrate fs, and the important is limit s to infinity. I am going to prove it. Take the RHS. What is the RHS? S to infinity fs ds. Now put the value of fs. What is fs here? Fs is 0 to infinity e to the power minus st ft dt. So put this value here. You will get 0 to infinity e to the power minus st ft dt. Now the outside function is ds. The limit of s is from s to infinity, and limit of t is from 0 to infinity. So if we change the order of this integration, by changing the order of the integration, you can write like this. We will discuss change of order in upcoming lectures. S to infinity, and I am integrating s function, st ds, and outside is ft dt. Very soon I will teach you what is the change of order of the integration. So it is 0 to infinity. Integration of e to the power minus st will be e to the power minus st. I am integrating with respect to x, so we have to divide by the coefficient minus dt, s to infinity ft dt. So it will be 0 to infinity minus 1 over t. You can take outside in the integral sign inside. As s tending to infinity will go to 0, minus as s tending to s, because it is the limit of s only. It is e to the power minus st ft dt. Some people also like written like s to infinity fu du, because they do not want to repeat the parameter variable inside also. So you can also use that notation, but we know that a to b fx dx equal to a to b ft dt. So there it will be no problem. 0 to infinity, it will be e to the power minus st into ft over t dt. So it is nothing else, it is the Laplace transformation of ft over t. Suppose, what is the Laplace transformation of my Anurag Shukla? Anurag. If Anurag is a piecewise continuous function and satisfying the exponential order function, then integration 0 to infinity e to the power minus st Anurag dt. So whatever function you are finding the Laplace, it should be written in this form only. E to the power minus st into that function dt. Provided the function is satisfying existence condition, then Laplace will always exist here. But even the function does not satisfy existence condition, in that case Laplace may also exist. I told you in that lecture 1 that also. Let's see one example based on the division property. This is the most important example. What is Laplace transform of cos at minus cos bt over t? Hence, I am also finding the real integrals now, which are difficult to find by simple method. Find the integration 0 to infinity e to the power minus t cos 2t minus cos 3t over t dt. If you use simple methods of integration, even gamma beta function will not help here, and because in the denominator you have t and multiplication trigonometric function. So by any of the method, whichever I have studied in the previous lectures are up to 10 plus 2, we cannot find this integration. Due to denominator, t in the denominator, we cannot find by integration by part because derivative of t will not vanish. And we know the gamma function, but due to trigonometric function here, cos 2t and cos 3t, it will be very difficult. We have to convert in the real and imaginary part. That will be some lengthy process, but in that case we can find it at least. But Laplace transformation, using Laplace transformation, this integration is very easy. So first we see what is the Laplace of cos at minus cos bt over t. So division by t property we will use. So first we see what is the Laplace of cos at. It is nothing else s over s square plus a square. I told you in the lecture 1. Laplace of cos bt is s over s square plus b square. Then the Laplace of cos at minus cos bt, use a linear property. I told you it will be Laplace of cos at minus Laplace of cos bt. So it will be s over s square plus a square minus s over s square plus b square. So this is the Laplace of cos at minus cos bt. I am not going to simplify it. It is representing fs here. What is fs here? This expression is fs here. Now if you divide by t here, Laplace of ft by t, I told you nothing else, it's the integration of fs from s to infinity ds. So Laplace of cos at minus cos bt by t will be s to infinity s over s square plus a square minus s over s square plus b square ds. So separate the integration, s to infinity s over s square plus a square ds minus s to infinity s over s square plus a b square ds. So if you suppose s square plus a square as v, its a derivative is present. So it is nothing else, it's the integration of 1 over 2 log s square plus a square, and s is from a to in s, limit is s to infinity, minus 1 over 2 log s square plus b square, limit is from s to infinity. You can find these integration are very easy by substitution. If you put s square plus a square equal to t, then its derivative is present. So now what will be the Laplace now? So Laplace of cos at minus cos bt by t is reduced as now 1 over 2 log s square log s square plus a square from a to s to infinity minus 1 over 2 log s square plus b square s to infinity. The limit are same, so we can write like this also. ln log s square plus a square minus log s square plus b square s to infinity. If you use the property log m minus log n, it will be log s square plus a square over s square plus b square s to infinity. Be careful in applying the limit. So upper limit is limit s tending to infinity log s square plus a square over s square plus b square minus log, if you put s in the place of s, there will be no change, s square plus a square over s square plus b square. As s tending to infinity, I told you in the limit chapter 15, this limit has coefficient 1 over 1 because the degree is same, so 1 by 1 limit will be 1 and log 1 is tending to 0. So this value will be 0. If you use my limit chapter, I teach you the limit result on the limit case. So it will be minus 1 by 2 log s square plus a square over s square plus b square. Take the negative sign inside. We know that minus log m by n equal to log n by m. So it will be 1 by 2 ln s square plus b square over s square plus b square. So this is a very useful result and important question. So now we have Laplace of cos at minus cos bt by t, cos at minus cos bt by t, which is equal to 1 by 2 log s square plus b square over s square plus a square. This is the solution. Now, what is the definition of Laplace of any function? It is from 0 to infinity e to the power minus st into multiplication of that function. So cos at minus cos bt over t dt equal to 1 by 2 log s square plus b square over s square plus a square. And what was our aim? 0 to infinity e to the power minus t cos 2t minus cos 3t by t dt. This was our problem. So put s tending to 1, s will be always positive. Remember here, a equal to 2 and b equal to 3 will give you the solution of this problem e to the power minus t cos 2t minus cos 3t over t dt equal to 1 over 2 log 1 plus 9 over 1 plus 4. So it will be log 10 by 2 means 10 by 5 means log. So 1 by 2 log 2 is the integration of this problem, which is very easy by Laplace transformation, but very, very difficult to find this integration using simple integration methods. I'm giving you one problem as a homework. Find Laplace transform of sine omega t over t division by t case. Let's see next property, Laplace of differentiation and integration. So we will see both the property here. First, integration property. If Laplace of ft is capital Fs and s is greater than alpha order greater than equal to 0, then the Laplace of integration of ft dt. Some people write f tau t tau for another variable. We can write like also this. This is nothing else fs over s. Fs over s. And s is greater than alpha greater than equal to 0. So this is the Laplace of integration. 0 to t ft dt Laplace is fs over s. We have to divide by s only for the integration case. Let's see what is the proof of this problem. Then we will see for differentiation also, because the integration result is useful in the differentiation case. That's why I am studying integration here. Let this function as phi t. So what is phi t here? Phi t is your 0 to t ft dt. Now what will your aim is now Laplace of phi t. Each question. This is your aim. What is the Laplace of phi t? Okay. So our aim is to find the Laplace of phi t. Phi t. Sorry for external disturbance. My younger daughter is very naughty, na? That's why we have to stop the recording due to some voice. Okay. So now our aim to find the Laplace of phi t. So phi t is your 0 to t ft dt. ft dt. So we will see together both the proof. Now I'm going to skip these two. I will see both the proofs together, differentiation and integration. So this is the result for integration case. Now I'm going to see the differentiation result. Let's see the differentiation result. So the Laplace of, if Laplace of ft is fs when s is greater than alpha greater than equal to 0, then Laplace of f dash t, derivative of this is given as s Laplace of ft minus f at 0. Remember f at 0. Or you can write Laplace s into fs minus f0, because I am assuming Laplace of ft as capital Fs. If it's second derivative, then the formula is s square Laplace of ft minus s into f0 minus f dash 0. Derivative of f at 0 is required here. Or you can write s square into fs minus f s into f0 minus f dash 0. Can you tell me the Laplace of third derivative? It will be s cube, then s square, then s, then degree 1, it means 1. Use the minus sign here, minus. It will be the Laplace of ft. It will be the f of 0. It will be the f dash 0. It will be the f double dash. Or you can write s cube fs minus s square f0 minus s f dash 0 minus f double dash 0. So this is the derivative result. You can go for nth derivative also. Now let's see the proof of both cases there. So going to prove for differentiation first. Laplace of ft is capital Fs here. I am going to prove for first derivative only. You can go by mathematical induction to prove the further result. It is equal to the Laplace of ft minus f of 0 or s into fs minus f at 0. Remember here, this is small f, this is capital F. This is the Laplace of the function. This is the value of the function at t equal to 0. At t equal to 0. Now, what will be the proof of this? Let's see. So if you use the RHS, so let's see what is the proof of this. LHS is Laplace of f dash t. It is 0 to infinity e to the power minus st f dash t dt. It is the Laplace of f dash t. We can replace f dash t here with the multiplication of e to the power minus st. It is the derivative. So I am assuming it is a second function because the integration of f dash t dt will be ft only, because it is dy dt of ft already here into dt, so it will become ft only. So what is the integration by part? First is outside, integration of second, so derivative of f dash t, then its integration will be ft only. from 0 to infinity minus 0 to infinity derivative of e to the power minus st with respect to t will be minus s e to the power minus st into integration of f dash t will be ft dt. So as you applied the upper limit, it will go to e to the power infinity, and ft is not growing faster than exponential function, so it will go to 0. Minus, as s tending to 0, it will become e to the power 0 is 1 f0. Minus minus plus, s you can take outside because we are differentiating with respect to t only, e to the power minus st ft dt. So can you tell me what is this? This is the Laplace of ft only. So s into Laplace of ft minus f0. F0, remember, f0 is important here. So you can write s fs minus f0 also. So this is the proof for the second derivative or nth derivative. Second derivative you have to use integration by part 2 time, and for nth derivative you can use the mathematical induction to obtain the main result. Now let's see the proof of integration case. So if Laplace of ft is capital Fs, and I'm going to prove in the previous case, then the Laplace of 0 to t ft dt is Fs over s. So what is the proof? Let's see. S is greater than 0 n. So we have assumed this function as phi t. So phi t is 0 to t ft dt. I am taking phi t as. Now our aim is to find the Laplace of phi t. So we can see that phi t is this. Now phi t is 0 to t ft dt, we can use Leibniz rule and we can differentiate it. So phi dash t means differentiation both the side. So t by dt of 0 to t ft dt, you can use Leibniz rule. I have already teach you. It is very useful result. Leibniz rule. Ft into derivative of t minus f0 and derivative of 0. It is only one function inside. So it is ft. It means phi dash t is nothing else ft. So if you use the Laplace of phi dash t, it is, use the differentiation rule, it is s into Laplace of phi t minus phi 0. Which result I am using here? I am using Laplace of f dash t. Suppose any function g dash t, then it will be s into Laplace of gt minus g at 0. Use the differentiation. It will work for any function ft, gt, phi t. So it is Laplace of phi dash t. Phi dash t is your ft only. Phi dash t is your ft only. And what is your phi t? Phi t is your Laplace of 0 to t fs 0 to t ft dt, small ft dt. Integration 0 to t ft dt, because we have assumed phi t at 0 to t ft dt. And what is phi 0? You can see phi 0 will be 0 because it will be 0 to 0 ft dt. It means this value will be 0. So Laplace of ft we have already assumed as capital Fs, then it is s into Laplace of 0 to t ft dt. So you can write that Laplace of 0 to t ft dt is equal to Fs over s. Please do proof at least 2 times so you will understand the proofs in the better manner. So this is the proof of Laplace integration and differentiations. Let's see some solution of examples I have given as a homework in the lecture 1. One is very important. Laplace, find Laplace of, I have given you 9 problems in the previous lecture. I am going to discuss one of the problem of greatest integer t. Greatest integer t. I have given this problem. What is the Laplace of greatest integer t? I hope you all have tried in your home, and you can ask the doubts in personally to me. Now, what is the Laplace of any function? Laplace of any function is 0 to infinity e to the power minus st ft dt. Laplace of greatest integer t will be 0 to infinity e to the power minus st greatest integer t dt. Now see, greatest integer function is piecewise continuous. Piecewise continuous. Not continuous at integers. At integers means equal to 1, 2, 3 and so on. So we have to break this integral at the integers using definite integration property. 0 to 1 e to the power minus st greatest integer t dt plus 1 to 2 e to the power minus st greatest integer t dt plus 2 to 3 e to the power minus st greatest integer t dt plus so on up to infinity integral. Remember, at 0, 1, 2, 3, we cannot find the value because it is not continuous function. So we have to see in the open interval. When greatest integer t, if t is between 0 to 1, the greatest integer t is 0. When t is between 1 to 2, greatest integer t will be 1. When it is between 2 to 3, the greatest integer will be 2 only. Because at 3 we cannot find the value because at 3 it is not continuous. Right hand limit is 3 and left hand limit is 2. So we have to take the values of the function where function is continuous. So inside these values function is continuous. Only it is not continuous at the integers. So it is 0 because between 0 to 1 this function is 0. 1 to 2 it will be e to the power minus st into 1 dt if the value is 1. Plus 2 to 3 e to the power minus st, the value is 2. Next term, you can write 3 to 4 e to the power minus st into 3 dt plus so on. So if you integrate it, you can find the value of this integration very easily. So it will be e to the power minus st over minus s from 1 to 2. Plus 2 times e to the power minus st over minus s 2 to 3 plus 3 e to the power minus st over minus s 3 to 4 and so on. If you simplify it, I am going to write the answer here. You will get it is equal to 1 over s e to the power s minus 1. I hope you all will complete it. So today I have given you some 3-4 problems and in the part 1 I have given you some 8-9 problems. Now you please try to finish all these problems. In the next part, we will study the Laplace transformation of some periodic functions and we will cover some important real integrals and we will discuss the definition of inverse Laplace transformation. Okay, thank you.